Today's a fun day. Ann and I are going to work some application problems, and then Candace is going to take us back into Graphland. I'm going to begin by working some quadratic applications. It was the 4th of July, and the happening place to be was Uncle Jeb's potato patch. Nephew Timmy had smuggled in some bottle rockets, but sadly for him, the first rocket Timmy fired was a dud. The rocket shot into the air and fell to the ground without blowing its fuse. Unfortunately for Timmy, his mother Marge did blow her fuse, and there were no more bottle rockets for Timmy that night. The height in feet, h, of the rocket, t seconds after it left the table from which it was launched, is modeled by the equation h equals negative 16t squared plus 75t plus 2.5. Let's answer each of the following questions about the flight of this dud of a bottle rocket. So here's our first question. How long after launch was the rocket 50 feet above the ground? So what's this question really asking us? This question is asking us, when did h equal 50 feet? So I guess we better recall our formula. So our formula says that the height t seconds after launch is given by negative 16t squared plus 75t plus 2.5. So I guess we have to solve a quadratic equation. We need to solve the equation 50 equals negative 16t squared plus 75t plus 2.5. My first objective when solving this equation is to make one side of the equation 0. I definitely prefer to have the coefficient on the squared term positive, so I'm going to make the right side of this equation 0. Adding 16t squared to both sides of the equation, I have 16t squared. Subtracting 75 from both sides of the equation, I have minus 75t. And subtracting 2.5 from both sides of the equation, I have plus 47.5. And all this equals 0. You know, I've got some pretty funky numbers in this equation, so I don't think I'm even going to bother trying to factor. I think I'm going to go straight to the quadratic formula. So the quadratic formula tells us that the value of t must be the opposite of b, so that's the opposite of negative 75, plus or minus the square root of b squared, so that's the square of negative 75, minus 4 times a, which is 16, times c, which is 47.5, and all of this is going on over 2 times a, so that's 2 times 16. I'm seeing some awfully big numbers there, so I think it's time to pull out my calculator. Now with my calculator, I think the first thing I'm going to investigate is the radicand, the discriminant, the expression underneath the radical sign. So let's see, underneath the radical sign, I have the square of negative 75. Well, that's the same as 75 squared. And then I have minus 4 times 16 times 47.5. Now, I don't think that 2585 is a perfect square. I can check that out by hitting my square root key. And sure enough, I was right. 2585 is not a perfect square because its square root is not an integer. When I make my future calculations in this problem, I want to make sure that I'm using exact numbers while making the calculation. Otherwise, I end up with something that we call propagated error. We have error built into further calculations which compounds the error. So I'm going to go back to the square of this number, and this is the number I'm going to write onto my screen. So let's see, we have 2585. That means that t is 75 plus the square root of 2585 all over 32, or t is 75 minus the square root of 2585 all over 32. Now I do want to convert each of these numbers into decimal form because 75 plus the square root of 2585 over 32 seconds doesn't really have a whole lot of meaning to me, and I suspect either for you. So, looking at the first solution, in the numerator, I have 75 plus 2585, take the square root, in the numerator, divide by 32. That equals about 3.93. In my second solution, in the numerator, I have 75 minus 2585, take the square root, done with the numerator, divided by 32, and that equals about 0.75. Notice that I'm using the squiggly equal signs because I'm approximating these two values. You know what we need to do next? We need to check. But before I launch into the numerical check, I do want to think, does it make sense that this applied problem would have two solutions? Well, Timmy launches the rocket from a height lower than 50 feet. The rocket goes up, and of course, it comes back down. So it does make sense that this rocket might have a height of 50 feet at two different times. But we do need to make sure that we check our numbers in our equation. So our two proposed solutions are 3.93 and 0.75. Both of these are approximations, so the height should be approximately 50 feet at these two times. Let's check that on our calculator. So I'm going to clear my screen, and I'm going to first check the 3.93 solution. So we're going to take 16, change the sign, times 3.93 squared, plus 75 times 3.93, plus 2.5. And the rocket's a little bit higher than 50 feet at this time, but that's okay because, again, our solutions were just approximations. Let's check the other number. So we have 16, change the sign, times 0.75 squared, plus 75 times 0.75 plus 2.5. Well, this height's a little low, but again, our answers were just approximations, so I think that this does check. Of course, we still have one more thing to do, and that's to write our solutions. So, the rocket was 50 feet above the ground, approximately 3.93 seconds and 0.75 seconds after it was launched. Here's another question about this rocket. How long after launch was the rocket 100 feet above the ground? So we want to know when was h equal to 100. Well, let's solve this equation. 100 equals negative 16 t squared plus 75 t plus 2.5. Just like in the last example, I think I'm going to make the right side of the equation 0. That's going to give me 16t squared minus 75t plus 97.5 equals 0. Again, just like in the last example, I think I'm going to use the quadratic formula to solve this equation. So that's going to give me t equals the opposite of negative 75 plus or minus the square root of the square of negative 75 minus 4 times 16 times 97.5, and this is all happening over 2 times 16. Again, just like in the last example, the first thing I'm going to check is the number under the radical sign. We call that the radicand, and when we're working with a quadratic equation, we call that number the discriminant. So, let's take the square of negative 75, which is the same as 75 squared, and let's subtract 4 times 16 times 97.5. Uh-oh, we got ourselves a negative number. In our proposed solution, it looks like t is 75 plus or minus the square root of negative 615 all over 32. This equation has no real number solutions. There is no real number square root of negative 615. Well, does this make sense in the context of the problem? Well, let's again think about this. Timmy fires the rocket from 2.5 feet above the ground. The rocket goes up, and then it comes back down. I bet you I know what it means that this equation has no solution. It means that the rocket never reached the height of 100 feet. So let's go ahead and write that as our conclusion. The rocket never reached a height of 100 feet. Let's ask one more question about this flight. How long after launch did the rocket hit the ground? So this time we want to know, when did h equal 0? So our equation is 0 equals negative 16 t squared plus 75t plus 2.5. This time, the left side of the equation is already 0. But again, I find it much easier to work with the quadratic formula if the coefficient on the squared term is positive. So this time, I really am still going to go ahead and make the right side 0. That's going to give me 16t squared minus 75t minus 2.5 equals 0. Again, I'm not even going to think about factoring this. I'm going to go right to the quadratic formula. T is the opposite of negative 75 plus or minus the square root of the square of negative 75 minus 4 times 16 times negative 2.5, and this is all happening over 2 times 16. So let's get out our calculators and see what our discriminant is. So we've got 75 squared minus 4 times 16 times 2.5, change the sign on that puppy, and we get 5785. So our two proposed solutions are t equals 75 plus the square root of 5785 all over 32, or t equals 75 minus the square root of 5785 all over 32. Let's get some decimal approximations for these two times so that the times make sense to us. So in the numerator of the first expression, I have 75 plus 5785, take the square root of that, done with the numerator, divide by 32, and we get about 4.72. Using the squiggly equal signs to indicate that this is an approximation. How about my second solution? Well, I've got in the numerator 75 minus 5785, take the square root, done with the numerator, things are looking a little bit suspicious here, divided by 32, and I see an e at the end of this number. That means that I've got some sort of scientific notation going on. I think I need to make my calculator a little wider. I don't think this trick will probably work with your calculator. And so it looks to me like what I have is negative 3.3 times 10 to the negative 2. That's the same as about negative 0.03. This time, do both answers make sense? I don't think so. T is how many seconds it's been since the rocket was fired. It doesn't make sense to be talking about what happened before the rocket was fired. So I think we're going to discard the negative answer in this case and just go with the solution 4.72. course, we need to check this. So let's get out our calculator one last time. And let's take 16, change the sign, times 4.72 squared plus 75 times 4.72 plus 2.5. And here we have that funny scientific notation again. This number is trying to tell us 4.56 times 10 to the negative 2. That's about 0.045, which is pretty close to 0. Close enough for our check because remember, our value for t was just an approximation. So let's go ahead and write our conclusion. The rocket hit the ground about 4.72 seconds after it was launched. I think that's about enough about Timmy's dud of a bottle rocket. Let's consider a different application. The width to height aspect ratio of a standard television screen is 4:3. The screen size mentioned in ads is the length of the diagonal of the screen. What are the height and width of a traditional 27-inch television screen? Well, it looks to me like we're going to have to turn this TV on before we're going to get anywhere with this problem. Now, I have a sort of diagram to model this problem in the corner of my TV screen, but I don't think that's a very good working diagram, so I think I'm going to simplify my diagram a little bit. Now I have a diagram that I can work with. I have a rectangular screen, and I have a diagonal. So the first thing I need to do is define a couple of variables. I went ahead and typed up my variable definitions so that I could speed up this lesson a little bit. Make sure you do write your own variable definitions. I decided to define h and w to be the height in inches and the width in inches, respectively, on the TV screen. So there's my h and w. What else do I know about this TV screen? Well, I know that the length of the diagonal is 27 inches. And if I look at the two sides labeled h and w together with the diagonal, I'm seeing a right triangle. And I know a formula I can use with right triangles. So I'm going to go ahead and get rid of the upper half of my TV screen. And I'm going to indicate that the length of the diagonal is 27 inches. And what's the formula I know about right triangles? It's called the Pythagorean theorem. And in this picture, the Pythagorean theorem tells me that h squared plus w squared equals 27 squared. The sum of the squares of the two legs equals the length of the hypotenuse squared. But there's a problem with this equation. And the problem is, it wouldn't matter whether I solved for h or solved for w. I'd have a variable in my solution. If I solved for h, my formula would still have a w. And if I solved for w, my formula would still have an h. So what I need to do next is I need to eliminate one of the variables from this equation. What other information was I given in the problem? Well, I was also told that the width to height aspect ratio of a standard television screen is 4:3. I can use this information to write down a proportion. The fraction w over h, that's another way of expressing the ratio w to h, equals the fraction 4/3. That's another way of expressing the ratio 4:3. Now, I want to use this equation to eliminate one of the variables from the Pythagorean theorem. In order to do that, I need to solve this equation for one of the two letters. I think I'm going to begin by using the cross multiplication principle. When you're solving proportions, you can get further in your solving process if you multiply the numerator by on one side of the equal sign with the denominator on the other side of the equal sign and set those two products equal to one another. That was a whole lot of words to say that 3 times w has to equal 4 times h. Now I need to make a decision. Which letter do I want to solve for? It makes absolutely no difference. I think I'm going to solve for h. that's going to give me h equals 3w divided by 4. Now there's a couple things that I can do with this formula. One thing I could do is in my picture, I could replace this variable h with the expression 3/4 w. But the other thing that I could do, and this is the really useful thing that I could do, is in my Pythagorean theorem equation, I could replace this h with 3w over 4, and then I would only have one variable in the equation. So let's go ahead and do that. So when I replace h with 3/4 w, my Pythagorean theorem equation becomes 3/4 w quantity squared plus w squared equals 27 squared. That's my working equation. That's the equation that I can solve. So let's work with that. So I'm going to begin by copying over my working equation that came from the Pythagorean theorem. 3/4 of w squared plus w squared equals 27 squared. Let's give ourselves some room and let's solve this equation. I think I'm going to begin by simplifying the first term on the left side of the equal sign. I can do that using my rules of exponents. I can distribute that exponent of 2 to every factor inside those parentheses. And that's going to give me 3 squared. I think I'm going to go ahead and move the w squared to the numerator side of the fraction bar, all over 4 squared. That plus w squared equals 27 squared. So 3 squared is 9, 4 squared is 16, so I have 9w squared over 16 plus, thinking ahead, I know I'm going to want to combine these terms on the left, so I'm going to write w squared with a denominator of 16, and that would be 16w squared over 16. All this equals 27 squared, so combining my terms on the left, 9 plus 16 is 25, so I have 25w squared over 16 equals 27 squared. Now you may have noticed I never did square 27, and you might have wondered why I didn't do that. Well, one thing is I have no idea what 27 squared is, but that's not really the reason I didn't square 27. Check out my coefficient on w squared. In the numerator, I have 25. That's a perfect square. In the denominator, I have 16. That's a perfect square. W squared is a perfect square. It's the square of w. And 27 squared is a perfect square. It's the square of 27. Consequently, everything's a perfect square, which means I'm going to be able to solve this equation without even reaching for my calculator. So, let's go ahead and isolate w squared by multiplying both sides of the equation by 16 over 25. That's going to give me w squared equals 27 squared times 16 over 25. And now let's use our square root property to isolate w. W has got to be plus or minus the square root of 27 squared times 16 over 25. One of our square root properties says that we can find the square root of each one of those individual factors underneath the radical sign and multiply and divide those resultant square roots. So this is going to be the square root of 27 squared is 27. 27 is the number that you square to get 27 squared. The square root of 16 is 4, and the square root of 25 is 5. So finally, when it's all said and done, I have 27 times 4 in the numerator, which is 108, and when I divide 108 by 5, I get 21.6. Now remember, we're working an application problem, and in this application, W is representing the width of a TV screen. So the negative number doesn't make sense in the context of this application. So I think our width is 21.6 inches. But we need to check this. So if W equals 21.6, then, well, we need to see what H would be. H would be 3/4 of 21.6. Now, we did some superhuman arithmetic on the last screen, so I think I'm going to cut myself a break and get out the calculator to figure out what this number is. So this is going to be 3 times 21.6 divided by 4. So that's 16.2. And what I need to do is I need to make sure that with these dimensions, the Pythagorean theorem is satisfied. In other words, I need to ask myself, does 21.6 squared plus 16.2 squared equal 27 squared? So let's get out the calculator. 21.6 squared plus 16.2 squared equals 729. Well, is that the square of 27? Well, one way we could check that is we could hit the square root key and make sure that we get 27. And sure enough, we do. So 27 squared is indeed 729. Our solution checks. So let's write our conclusion. A 27-inch TV screen really has dimensions (21.6 inches by 16.2 inches. Let's work one last problem. The height of a certain trapezoid is the same as the length of the shorter base of the trapezoid. The longer base is 3 centimeters longer than the shorter base. The area of the trapezoid is 15 square centimeters. Find the dimensions of the trapezoid. Now, this is a pretty mathy-math type problem, and you might be wondering why I'm choosing to work this problem. It's because trapezoids do show up periodically in word problems, so it's a good idea to keep base with trapezoid math. So let's do some trapezoid math. Let's first recall what a trapezoid is. A trapezoid is a four-sided closed figure that has the property that two of the sides are parallel to one another. The two parallel sides are called the bases of the trapezoid, and the distance between the two parallel sides is called the height of the trapezoid. So the first thing we need to do is remember which pieces of the trapezoid were referenced in the word problem. And the pieces of the trapezoid that were referenced were the lengths of the two bases and the height. So we need some variable representations for each of those pieces of our trapezoid. Let's define x to be the length in centimeters of the short base. I made that decision because the other two lengths were made in reference to the length of the short base. For example, we were told that the length of the height is the same as the length of the short base. So if x is the length of the short base, then x is also the height. And then we were also told that the longer base was 3 centimeters longer than the short base. So the length of the longer base is going to be x plus 3. Now, what else were we told about this trapezoid? We were told that the area of the trapezoid is 15 square centimeters. So what we need to do is recall what the area formula is for a trapezoid and set it equal to 15. Now, chances are you probably don't remember the area formula for a trapezoid, but I'm sure it's written down in your book somewhere. I've been teaching math for a long time, so I do remember that the area of a trapezoid equals 1/2 times the length of the height times the sum of the two base lengths. So let's use this formula in the context of this problem. In this problem, we know that the area is 15. We know that the height is represented by the letter x. we know that one of the bases is also x, and the other base is x plus 3. Let's solve this equation. First thing I need to do is simplify the right side of the equation. So when I do that, I'm going to get 15 equals 1/2 x times 2x plus 3. Then I can go ahead and distribute 1/2 x through the parentheses. That gives me 1/2 x times 2x. Well, 1/2 times 2 is just 1. X times x is x squared. And then I have plus 1/2 times 3 is 3/2 x. Now, regardless of what method I ultimately use to solve this equation, it's going to be easier if I clear the fraction. So let's multiply both sides of this equation by 2. When I do that, on the left I'll have 30. And on the right, making sure I distribute 2 to both terms, I'll have 2x squared plus 3x. Let's make the left side of the equation 0 so that the coefficient on x squared is positive. 0 equals 2x squared plus 3x minus 30. And I'm not going to even think about how this factors because my leading coefficient isn't 1. I'm going to go straight to the quadratic formula. X is going to be the opposite of 3 plus or minus the square root of 3 squared minus 4 times 2 times negative 30 all over 2 times 2. Let's go ahead and find the value of the radicand. So the radicand, the expression under the radical, is 3 squared minus 4 times 2 times 30. Change the sign. All that equals 249. Is that a perfect square? No, it's not. So I want to leave it squared until my final calculation so that I get exact values. So what are my two proposed solutions? Well, x could be negative 3 plus the square root of 249 over 4, or x could be negative 3 minus the square root of 249 all over 4. Now, before I go and get my decimal approximations, I'm going to make a little observation. And that is that in this second proposed solution, both terms in the numerator are negative. So the decimal approximation of this second solution is destined to be negative. Well, what is x representing? It's representing a length. There are no negative lengths. So I don't need to even bother getting a decimal representation of this number. There's no way this is going to be a valid solution in the context of the problem. But I do need to get a decimal representation of the other number. So in the other number, in the numerator, I have 3, change the sign, plus 249, take the square root, done with the numerator, divide by 4. And I get about 3.19. But you know what I need to do? I need to check this solution. Plus, I also need to find the other pieces of the trapezoid. So here's my trapezoid, and my proposed solution for the length of the shorter base is 3.19 centimeters. Well, the height has the same length as the shorter base, so the height is also going to be 3.19 centimeters. And the longer base is 3 centimeters longer than the shorter base. So that would make the longer base 6.19 centimeters. Well, let's make sure that with these dimensions, the area of the trapezoid is about 15 square centimeters. Again, it's only going to be about 15 square centimeters because I'm approximating my solutions. So using these numbers, the area is going to be 1/2 the length of the height, which is 3.19 centimeters, times the sum of the lengths of the bases. The sum of the lengths of the bases here is going to be 9.38 centimeters. So we're going to take 1/2, which I can represent as 0.5, times 3.19 times 9.38. and that equals pretty darn close to 15. So I'd say that our answer checks. So let's write our conclusion. And our conclusion is that the base lengths of the trapezoid are 3.19 centimeters and 6.19 centimeters, and the height is 3.19 centimeters. That's it for me in applications. Anne's up next with some applications of her own.